Alright guys, so for my course you have options to pick for what you want to do past the 8 required blocks. So I wanted to do a brief video that explained what each one of those was so you can make a more informed choice about which ones you wanted to do. I'll also kind of explain the purpose of the required blocks so you know kind of why you're doing what you're doing. Alright, obviously the software overview is pretty obvious. It's just get you kind of wading into which software pack you picked and get you started on understanding how the software works. The basic stats review covers all of like an undergraduate stats course almost. So t-tests are really important to understand because they're the building block for ANOVAs. And they're part of the post hoc test for ANOVAs. So t-tests are used whenever you only have 2 groups. And you just want to know if these 2 groups are different. Now these 2 groups might be different groups of people, where you have one group you gave some drug to and another group you didn't. Or it might be 2 time points. So pre-test post-test design is a dependent t-test. We're really interested in the change scores of people, or if they have 2 scores on scales and you want to know if those scales are different. So there's kind of t-tests are for whenever you only have 2 measurements of some sort, either between groups or within groups. The other thing the basics review covers is correlation. So correlation is the building block for regression. And most people are aware of what correlation is, but it allows us to look at 2 continuous variables at once, analyzing the relationship between them. Do they go up together? Or do they go down together? Whereas t-test really focuses on groups or time points of designs. Now, I find graphs to be very important because null hypothesis testing, which is what most of this course covers, has a lot of flaws. And so one thing you'll see me talk about across all of these videos is the basic gist of null hypothesis testing being a ratio of good variance to bad variance, or sort of what we think happened to error, but also how to report your data in a way that doesn't obscure the data. So graphs to me allow a reader of research to really view the data. And so we'll talk a lot in each of the other videos on how not to distort a graph, how to present them in the most appropriate way, giving people the most information, the best bang for their buck, basically. So covering a special section on graphs really leads into the rest of the analyses where we'll do a graph for each one and be able to present our data in a publishable way. Data screening is also a very important building block for the rest of these analyses. And this allows us to check for assumptions of the tests we're running. So nearly everything we're going to do is a parametric test. There are a couple of exceptions. And what that means is that it has a lot of assumptions about the dependent variable. Excuse me. So we expect that dependent variable to have specific criteria that have been met. Excuse me, before we get to running the analysis. And so understanding how to screen your data for outliers or missing data or accuracy problems is really crucial to having the analysis that you run be appropriate. So it's sort of like garbage in, garbage out. If the data that you have has lots of typos or has a lot of problems, the answer that you get from an ANOVA is useless because it doesn't mean what you think it means because you have all these errors. So we're just going to talk about how to fix errors. So those 2 building blocks apply to the rest of the analyses that you'll do. So in every video, pretty much every video, you'll see me talk about how do I screen the data for this type of analysis specifically, and then how do I make a chart for that type of analysis. You'll also see effect size integrated very heavily into all of my videos because we want to, even if we're going to use null hypothesis testing and p-values, we want to make sure that the data is accurate and meets our assumptions. So data screening, we want to make sure we present something alternative to those p-values. Those are effect sizes to really judge the practical importance of our results. And we want to present the data in the best way possible, and that's graphs. So all of this ties together in my push for, yes, we're still using ANOVA, but there are all these other things that we can add to that to supplement for people who aren't really interested in p-values. All right, so then when we get into the real analyses, I made several of these blocks required because there are just certain things that you see across the literature no matter what focus you have. So we've kind of got three different kind of groups of people in our course, but no matter what, ANOVAs are a thing and regression is a thing. So I picked these other required blocks because these are things that just anyone who understands stats, at least a little bit, needs to know. So a between subjects ANOVA is really focusing on when you have more than two groups or two levels and you just want to know the differences between them. So you might have three different groups of people that you tested for something and you just want to know if their scores are different. So we might test different drug dosage levels and look and see if their outcome scores are better. Or you might give people, for athletic training students, you might give them different stretching exercises. So each group did a different type of thing, and did their scores, flexibility scores, get better? And so that will be a one-way between subjects ANOVA if each group of people is different. Contrast that with a one-way repeated measures ANOVA, where everyone takes everything in the design. So in my stretching example, it might be week 1 you had them this type of stretch, week 2 you had this other type of stretch, week 3 you did something else. Then you looked at their scores across weeks. That would be repeated measures. So the big distinction between these two, other than some math, is that in between subjects ANOVA, we're really looking at different groups of people. And in repeated measures ANOVA, they're the same people tested multiple times. So anytime you have a pre-test, post-test, 6-month design, that's repeated measures. The one-way part means how many variables you have. So one-way ANOVAs have one independent variable. Two-way ANOVAs have two. And this is where we get into talking about interactions. So how do two variables interact with each other? The required one is a two-way mixed ANOVA. And I did that because I figured if you could figure out a two-way mixed ANOVA, you could probably do the other two types of ANOVA. Because two-way mixed have some special considerations. Because it depends on what variable you're analyzing. And that'll make more sense when you get to it. But a two-way design just means I have two independent variables, so I have to think about interactions. So you'll learn about how to deal with interactions in ANOVA. Mixed means there's one of between subjects and one repeated measures. Some other choices that you have that are not required are two-way between subjects, where you have two independent variables and they're all different groups. And a two-way repeated measures, where you have two different variables and they're all the same people. So you're testing them on two different things, but they're in every single option. And so the distinction here for all these different ANOVAs, one-way means one IV, two-way means two IVs, between subjects means they're all different groups, repeated measures means they're all the same group, mixed means half and half. So you could pick either of these two options, and if your thesis or seminar project or just a project you're working on requires one of these, I would suggest using those as your examples, because they are slightly different than doing a mixed ANOVA, but I think if you can figure out a mixed ANOVA, you can always figure one of these out later. The other great thing about putting all of this on YouTube is that, let's say a year from now and you're trying to work on your thesis and you can't remember, you can always come back and watch these, since I have everything open to the public, and your advisor goes, oh no, this is a two-way design, you need to learn how to do that. You can watch one of these later as well. Alright, so let me scroll up here. Some other ANOVA-ish designs, these two here, ANCOVA and MANOVA, that are optional. So ANCOVA, the C there is the important part, is a design that's halfway between ANOVA and regression. So ANOVA really uses categorical IVs. So time points are considered categorical, or grouping variables are categorical. And then your DV is continuous. With regression, what we can do is mix and match types of variables. So I can make some categorical, some continuous, all continuous, I can mix and match. So regression is actually more useful than ANOVA sometimes, but lots of people still like ANOVAs, so definitely going to cover those. So ANCOVA is halfway in the middle. ANCOVA is an ANOVA with a continuous variable as a control. So that's why this C is important. It's a covariate or a control variable. So what happens is you control for something first that you know is different across people, and then run an ANOVA. It's kind of like an ANOVA with an extra step. So a good example of this is like if we're going to analyze how people do in our study sessions, we might consider controlling for their previous GPA, because students all have different kind of smart kid factors, we jokingly call it sometimes. So we might control for ACT or GPA or something first, and then look at how those study sessions improve their grades. So we can kind of level the playing field. So ANCOVA often is about controlling for continuous variables that you know make the thing you're interested in uneven to start. MANOVA is multiple ANOVA, but it's not like running 6 ANOVAs. It kind of is, but it's multiple DVs. So instead of having one dependent variable, you might have 6, and they're all related. And so you can run a MANOVA to look and see if people are different on a kind of combined score. So MANOVA is really useful for people who might need to run a lot of ANOVAs but want to try like one big design first. So this is when you have multiple measurements that are separate things and they're not repeated. So MANOVAs, sometimes people use it for repeated measures, maybe not the most appropriate thing, but this is more of a case of I have multiple DVs instead of multiple time points. The last required block is regression. So you're going to do multiple regression, a hierarchical regression. Multiple regression just means there's more than one variable, because if there's one x and one y, it's correlation. So multiple regression means I have like 2 x's and 1 y. It's always one dependent variable. Hierarchical regression is when you do things in steps. So I want to first control for these variables. So that's why I said ANCOVA is like halfway in the middle. And then I want to run this next thing. Well, what happens if I add this next thing? So you'll learn how to test variables in steps. So do this one first, then this one, then these other ones. Now, all of the rest of these are optional. Whoops. And so let me just kind of explain what those do. Moderation and mediation are kind of tied together. If you're going to do one of those, you might as well do both of those together. They're related to each other. So moderation is interactions in regression. So when you're interested in how two variables interact, but they're continuous. Mediation is, I always think of this as the way it sounds like the lawyer style, is the third wheel kind of issue. So does one variable change the relationship between two other variables? And running those, they're like conceptually very different, but running them is kind of similar. So I'd say if you're going to do moderation or if you're going to do mediation, I'd actually tell you to do both. So you don't get them confused, because you can learn both of them at the same time. So moderation is interactions in regression. Mediation is understanding the third wheel relationship. So how does 1 and 2, the relationship between 1 and 2 change if you add 3 to the equation? Log regression might be very popular for our sort of medical focus group, because I see a lot of that in that literature. So in log regression, what you're doing is you're predicting a binary outcome. So let's say you want to predict whether or not someone will relapse for whatever reason. And so what you can look at is predicting sort of a yes-no variable. 90% of this course is parametric statistics. We're predicting some sort of continuous dependent variable. Log regression is non-parametric. We're predicting a categorical variable. So I'm predicting which group you're going to go into based on a lot of other things. Someone who is in the psych department actually uses this a lot, and they're predicting how a jury will vote. So will they find them guilty or not guilty based on a bunch of different things. So log regression is where the dependent variable is categorical. Now, there's 2 of these. That is not one that you can do very easily in JASP. I think there actually might be a way to do it, so that there might change by the end of the semester. But for right now, it doesn't look like it quite does log regression. Okay. Now, multi-level models are definitely something you cannot do in JASP at the moment, so you can kind of tune me out if you picked JASP. But those are ones where I have a structured set of data. Okay? And you're thinking like all data is structured. But what I mean by this is data that is repeated across participants. So I'll give you an example from my own research. We tested last spring looking at how people felt about their exams before they took them. So before each exam, we gave people a question that just said, how well do you think you'll do on this exam? So we had 4 of those across the semester, looking at just how they thought they would do. And then we measured their performance on the exam. But each exam had X number of questions, 10, 20 questions. So that data is structured where I had people in 2 different classes who then each took 4 different exams, and each of those exams had a bunch of different questions. So that kind of creates this structured data set. Sometimes it's called nesting. A multi-level model allows you to control for that sort of design. So really it's a useful analysis if you're going to have lots of different repeated measures variables. And so if you are thinking about using things that are going to be repeated or anything with lots of items, I highly recommend MLM. It is becoming more popular because it's slowly getting easier to do. It's one of my favorite new analyses, and it allows you to control for structured data. Exploratory factor analysis, this is a favorite. Everybody loves EFA. It is very different than the other types of designs that we do. I'm guilty. I love EFA as well. So if you're wanting something that'll be kind of different and fun, I'd say EFA is your friend. And what it does is it allows me to look at how things are related to each other. So it's kind of correlation on steroids, where I can take a questionnaire. So I have this questionnaire, it has 10 questions, and I want to know if those questions all are related to each other or if one of those is an odd man out. And so factor analysis lets me group questions together that are all similar and then ditch the bad questions. So I do a lot of factor analysis, and we're going to really focus on it from a scale development perspective. So how do we create the best psychometric scales, but also allows you to test other people's scales or just kind of look at how things hang together. So for our med people, you might have a bunch of different tests that you give someone, and you want to know if they're related or not. That might be a good way to test EFA. Now, specifically for our med group people, this doesn't preclude people who are interested in psych, though. Kind of a couple of blocks of things that are more in the medical field. So chi-square is an analysis where both variables are categorical instead of one being contiguous and one being categorical. This time, both of them are categorical. And so we'll talk about proportion tests where you can compare 2 different percent rates to each other, or in a couple of ways. An independence chi-square where I can look at 2 categorical variables. And then to me, one of the best things that we can do is Fisher's test. So Fisher's exact is when you are testing a chi-square with very small numbers of people. And often, when you're working, maybe working with sports teams or working in the medical field, you just can't get enough participants. And so Fisher's test really allows you to work with a very small sample size. McNemar's test is for repeated measures chi-square. And so that all together is kind of grouped together into this chi-square bundle. And all of those are really great for categorical analyses. When you're looking at outcomes for participants that are sort of yes, no, or this group or that group. So to give you an example from something I've done recently, we looked at ethnicity/race and the likelihood of developing 2 different types of skin cancer. And so they either got one skin cancer or the other, and then they had race. Those are both categorical. So we were able to use Fisher's test because you can't make people have skin cancer, so there's a limited sample there. All right, what I've called clinical block 1, because I don't have a good name for it, is looking at kind of test rates of different diagnoses. So we have sensitivity and specificity is kind of the big part of that. So sensitivity is the ability of a test to correctly identify whatever you're looking for, usually disease rates. Sometimes this is called true positive rates. Specificity is the other way around. It's the ability of a test to correctly identify people without the disease or thing you're looking for. So they go together. Predictive value is like kind of tied to that, so how well it's going to predict those kinds of rates. Likelihood ratios are the ratios of two different options together, so it's kind of like odds ratios, how likely something is to happen. I think about likelihood ratios in reference to sports betting. And then ROC curves are in this block because it's a receiver operating characteristic, right? It's a plot that kind of plots sensitivity and specificity against each other. So that whole thing is kind of all tied together, and there's a reason for that. You can't do this in JASP, but you can do this online, and all of them online, it's all one web page. And so it's very easy to get. It's a beautiful website that allows us to calculate everything together. And then in the second clinical block, we're going to talk about odds, ratios, risk, and numbers needed to treat. So kind of a separate set of issues that people deal with when they're looking at clinical outcomes. So those are all the options that you can pick throughout the semester. Everything is slowly getting posted to Blackboard because I can only make so much happen in one day. But if you have questions about any of these designs or what might be best for you, given what you want to do, certainly contact me. I'm still making the rounds each week, trying to meet everybody and get faces to names. And then I will gladly help you decide what options you should do to really focus on what you're interested in.